just look at the notion of IPC. And see a design space. So you guys, so we've seen our points. Okay, and each point represents some class of systems. Okay, we saw RMI, and it represents a class of remote procedure call systems. And we saw pipes and Xenu and NIO and sockets and serialized streams. So we saw a bunch of systems. Okay. And design space would mean what? We systems guys like to think we are mathematicians, so we say, okay, there's these dimensions. And dimensions in mathematics are orthogonal. In computer science, they never are. The choices you make along, or at least in systems, in one dimension influences what you do in another dimension often. But it's nice to sort of try to be somewhat abstract. Okay? And what would these dimensions correspond to in systems? I mean, in mathematics, we have X, Y, Z plane, we define all these, yeah.
We talked about like RMI versus NIO, and programmability versus the abstraction.
Okay, so there are these issues and there are these trade-offs, right? So in general, each of these represents basically an issue. Programmability, performance perhaps, or a function. Okay, memory management versus, which is also like an issue. So let's just take something that we're all familiar with. So the dimensions are issues, and that's why it's not really mathematical. But values are approaches. Okay? And I know a lot of you guys, all of you guys, to get a PhD or to get a master's have to do a paper, right? And you can blame me for that. Before this paper, does anybody know what the requirement was to get a master's? There were these famous CCEs, core comprehensive exams. We had a set of core courses. Everybody had to take the same set of core courses. And then there were these exams that they had to pass. And I argued that, look, firstly, there is no such thing as core. And secondly, you've already been, I'm big for exams. Okay? I came from a system that rewarded exam takers. So in fact, I did a PhD to see whether I could do anything else but an exam. Because exam means what? In 2 hours, I can outthink the other person. What can I do? In 3 hours, that person could probably do better than me. And in 6 years or 5 years, they could probably. So that was the big question I had. So exams are great and they have their function. That's why we have exams here. But if you've been tested once, why do it second time, right? And they were really like final exams. So I said, look, but they all wanted some kind of core, some kind of comprehensive. The university wants that. So I argued that, look, if we do some kind of paper that integrates information in some way from some broad area, then that should satisfy. And then we can also go in. That can also lead to a PhD. And why am I bringing this up here? You can write papers in many ways. You can say, okay, I'm going to cover these 3 papers. And I'm going to say the first paper said this, the second paper said this, the third paper said this, and that's a composition of 3 papers, summaries. And if you're going to do a single paper on 3 different ideas, you need to abstract them out somewhere. And one way to abstract that out is to basically do it seamlessly, where you say, this is a design space, this is the approach, these are the dimensions, these are the approaches. And then by the way, say, that system, that paper, it falls here. It makes this choice along this dimension and this choice along this dimension. And that just becomes a side effect. And honestly, when I teach, I really never teach from a book. So I have read the papers, and you don't see the seams, but that's because I'm trying to do something like this. Normally, you didn't quite see that in this course, but in other courses, that's what I try to do. Because I started with some systems just to give you guys some background. If I'm doing OS, you guys sort of have seen an operating system, at least used it. You don't have to go too much. So think a little. I'm going to make you guys think about the design space, and when you guys do your integrated papers, think design space. That is the way to do a paper, a comprehensive paper, where you say, this is the topic I have, which is a topic that covers all 3 papers or 5 papers. And this is the topic definition from which these issues arise. And again, these issues are some, intersection, union, some combination of issues you saw in the papers. and say, you can go this way and there's a trade-off here, and you can go this way and there's a trade-off here. Rather than saying, this paper improved on this paper, improved on this paper. If you do it that way, you might as well present the last paper. I mean, that's fine too, you sometimes get some history. But you haven't done much because the third paper probably referenced the second paper, and which probably referenced the first paper. So you haven't done any integration of your own. And you're just taking the integration that was given to you. Whereas the real challenge in research or in writing is to take three things that were not meant to be combined. I mean, that were meant to be combined perhaps, but were not combined, and you did the combination. Okay? So I just want to put a spiel for that that's the way to write, that's the way to present, that's the way people enjoy things. Okay? So we're going to try to do is, based on what we have seen already and what might exist in other systems, we're going to try to dimensionalize, if you will, the IPC design space. And this is, everything we did after RMI is sort of, there's some, it's sort of my research, some part of my research is my idea. So don't think this is all well agreed on. So challenge me like crazy. Okay, there might be inconsistencies here, but this is my attempt to basically combine things that I have seen in papers and my own systems. Okay, and even, yeah. Okay. So I'm going to do, this is a very challenging, I'm going to do this in two, and again I'm saying that, this idea is not something we see in OSs, for instance. Okay, there's memory management, scheduling things, synchronization. In compilers, we see there is scanning, parsing, code generation, various kinds of optimization. So we tend to, as educators, naturally go to these design spaces. Okay? And so, the word naturally is one of these words you want to never use in a paper. And, what's natural? I mean, when object-oriented programming first came in, people just didn't know why it was good. And everybody said it's natural, it's natural. And, it's natural, but it's not that natural either. You try doing it well, and it's very hard. And so, why do academics, or why do we gravitate towards design spaces? Why did I go and say, don't have this seamless thing, have the seamless thing. Don't have the seamful thing, have the seamless thing. Why are design spaces useful?
Gives you some form of metric. What kind of, it helps you quantify what trade-offs.
So maybe it helps you quantify. If you can figure out the issues, then there are some ways to measure how well you meet the issues, and then the approaches you have can be evaluated against each other. So it's a way of comparing and contrasting systems. If I say, this is Windows, this is NT, this is Apple, I mean, what did you learn? You want to know what's different, right? We all learn by diffs. Firstly, we learn by diffs, and we evaluate also. We want to evaluate also. So I want to know, how is it different from what I just learned last? How is C++ different from Java, and how is C++ different from Smalltalk, and then I sort of understand the whole thing. So that's why I said we academics naturally gravitate towards this stuff, because we want to evaluate things, we want to understand things. Okay, so we do it this way. Other reasons, you're a practical guy, and you want to just build nice things.
It's easier to talk about if you can sort of have a common vocabulary where a word like sockets is easily understood by multiple people, and they all have sort of the same understanding of it. Instead of saying, well, I'm just going to create this sort of object that lets me open up a stream between like one remote computer and another.
Okay, so if we can,
I'm just going to make a socket.
If you're going to create some abstract notion of a socket that is implemented by Java and Unix and all the other systems, rather than say, this is the API that Java has, and this is the API that, and we're calling it this Java socket object, and we are calling it this Unix socket thing, sure. So that's the value of abstraction. That we again, is something to do with diffs, that we want to know what the basic idea is. And maybe we can say that, in Java we can't do this, but in Unix we could do it. If I want to describe to you a set of concepts in this one semester, will I be faster this way, or will I be faster with single points? Can I cover more ground through design space? I don't have to repeat things, right? I've covered the thing once, and I've said these are the dimensions, and then I don't have to go and enumerate all the points. Okay, so that's, common mechanisms and issues, abstract. Okay, what about this? Einstein always wanted the grand unified theory.
Things talking to other things.
So Sorry?
It'd be a great title for 4 weeks on
So, if you want to have a paper that says, like I told you, a high-level and flexible system to do this, how are you going to say that you're flexible? You're going to say you're flexible by saying that you cover a part of the design, some large part of the design space, right? You're flexibler or more flexible, right? Which means that part of the design space you're covering is more than the design space covered by someone else. And that is a goal to have. And I've always said that there's a trade-off between high level and flexible. So maybe I can design a system in which all these other systems were in some sense special points. That's my Einstein's grand unified theory. And maybe it's going to be such a stupid system which doesn't do anything right. And I've told you guys about attempts at such systems in other fields, in operating systems. It was? What was I just going to say before that? Oh, I guess you guys... Which system tried to do everything? What is the opposite of Unix?
Oh, Xenu.
No. Right, okay. That's one way. I used to give questions to my operating system exams. If, if Unix is a mammal, what is Xenu? Okay, that was sort of, or what one particular, no, I don't know if I said mammal, I said human being, and Xenu is in one extreme. And what is the other extreme of Unix? When Unix was derived, it was not. You guys said that once in your class. You knew this. Multics?
Oh, yeah, sure.
Okay, it was not Multics. Multics tried to do everything in operating systems, and I love it because I really understand how things add up. And in programming languages, did I mention a language that tried to do everything? Ada. Okay. Ada was a language that tried to do everything. In architectures, there was a system that tried to do everything, which was Intel 432. And Ada was meant for Intel 432. Intel 432 never quite worked. And Ada was used by defense, and is still used by defense, by the way. I went to a conference where there were Ada people from military that were advertising Ada. So it's not a dead language. But so, before I go and say why this is great, I'm going to say that this can be bad. But even if it's bad, we've at least understood how things, I can talk of design spaces in the abstract, but when I go in and see them implemented in one system, at least I formalize it. Even if it's a lousy formal system, it's a formal system. Okay, and these two things sometimes do go together. Okay, so abstract model to cover all of them, and basically you can probably have an implementation of the model also. So I can I can try to do that. So we could try to have this grand unified system where we don't have to get into religious wars about, whether this is the way to do it or that is the way to do it. We can just have one system that does it all, and you choose. Okay. So let's go and see what the scope is. Okay. Great title for the course is Things Talking to Each Other. So we're talking about distributed programs. We're talking of some kind of inter-process coupling, right? Which implies some form of process communication. And we'll just go and even though we are distributed systems people, the things are very similar in communication between lightweight processes or threads and heavyweight processes or regular processes. Okay, so we'll cover both, just to be well complete. But I'm going to use some mechanisms that were designed purely for threads and help them understand, help you contrast what you've learned with those systems. Okay. So I want to put these all guys in one design space, but before I do that, I'm going to do something simpler. There is something that unifies all of them, which makes them different from something else that you might know, that also gives you some way of coupling processes. So rather than trying to figure out what the differences are between them, try to unite them and say, how are they different from some alternate universe that we haven't even seen, or maybe more than one alternate universe. Is there some kind of inter-process coupling that we haven't even covered here? That's fundamentally different from this. Now, maybe nothing is really fundamentally different, but yes, some form of IPC. Okay, that's good. That's good. DMA is sort of has to do with devices and computers. So yeah, you're thinking multiple computers, but basically MA. You know, if Zach was here, I would say, what do you learn in Jan Prince's class? And he would learn a lot of shared memory. Okay? And that's typically, the reason you said DMA was because you're saying one computer accessing the memory of another computer, which is what it would translate to. But at least sort of in one process, you could have, you know, we're trying to communicate information among processes. So one guy, write, basically you want to send some information, you write to this object, some shared, by object I really mean some shared block memory. Okay? And you consume information by reading from it. Okay? And if we don't have to worry about the fact that, you know, there are multiple address spaces and you know what to do in that case, and there are solutions that capture this idea in distributed programs, is that a good abstraction to have? So when I'm going to do this design space, I'm not just going to present to you a design space and say, here it is. I mean, you know, I can always imagine a rectangle OV, right? It's not a very useful thing to imagine. So we'll try to go and justify each point of the design space and say, you know, these are the pros, these are the cons, this will get to the metrics we were talking about. So, like I said, you know, in Jan Prince's class, I'm sure they're covering a lot of this kind of stuff. And what are the pros and cons? I mean, this is something that we all learn, right? One of the first few things we teach our students is global variables. Also, we try to tell them not to do global variables. But then we say there are instance variables that are okay. So, you know, we kind of schizophrenic about this stuff.
It's less structured than other purposes. It's like, if you try to like, make an analogy to, you know, global variables, then there's a sense in which stuff can change and you're not really aware. It's also kind of hard to reason about because there's no guaranteed way in which things are modified.
There are fewer guarantees.
Right.
Who knows who will access them? And that's why you want to pass things as parameters if possible. You don't want to go and set, you know, 2 global variables and say, okay, procedure, go and work on those. If that procedure is the only one that's going to use them, just pass them as parameters, right? So things are less structured, and in terms of you're building your distributed simulation. Let's say you had global variables.
It's not a huge
Synchronization issue that, you know, multiple people can change at the same time. And how does the receiver know that something has changed? You could do some weight on a semaphore. Okay? And so by itself it's not. So, you know, and by the way, this is not a stupid idea. Okay? You're trying to multiply 2 matrices. Each thread is trying to go and compute some different value of the matrix. Each one just writes it. And at some point, you know, that value is read. Okay, and maybe at that point some semaphore can be signaled. Okay? And how does information consumer get notified about new information? You know, you could use semaphores, conditions, there's all kinds of value ways to do it. But that's another mechanism you have to add on top. And if the receiving process needs that information, it has to block for it. We'll see there are ways to receive information that don't involve blocking. Okay? So these are some issues. And of course, you know, what happens with threads in different processes? Well, you know, what you could do is just wrap some process around that shared object. Okay, and then of course, how do you communicate with that? Well, there's just, you know, underneath. It's not exposed to the programmer, but underneath you're doing this. And I read a thesis which allowed, I told you guys, remote assignment. Okay, just underneath you use some networking primitives to go and send messages and get back. Okay, which is a form of DMA essentially. Okay. So you need some other mechanism to communicate with the process, and like I said, it could be your network messages. Okay. So shared memory pros and cons, familiar model. Okay, that's a big deal. I mean, by the way, there's been a big war between shared memory and non-shared memory, and you know, this is a familiar model. Not quite sufficient when threads are on different computers unless you do something else. Global variables are considered bad because of all the reasons. You know, you can't reason very well about them. You know, threads other than the reader, you can't control who accesses them. Okay, so we're going to see about the script access issue. That's going to be a big deal. So, okay. and the receiving thread must either wait or poll for information, unless we build some notification mechanism on top of this. Okay. So do you guys know of some notification mechanism in operating systems that's other than what I've seen, like what we've seen, sockets and NIO, something that's very fundamental and it came very early in operating system design, before things like sockets were around? You all know it. I'm just trying to see whether you can later. Some way of one process notifying another process. And I use the word notify because the other word I was going to use was going to just give away the answer. What are some synonyms for notify? Sorry?
Interrupt.
Very good. Excellent. Can one process interrupt another process in operating systems? And what is that called in Unix? When a process interrupts. So how can a process interrupt? A hardware can interrupt the soft operating system. We know that. That's called a hardware interrupt. We'll say something is a software interrupt, and here I'm being a little different from what Intel uses terminology. Okay? I'm going to use the word software interrupt. When one process can interrupt another process. That's not how Intel uses it.
Are you talking about like fixed signals?
Notify, interrupt, signal. Okay? So, and what is the signal what is the signal API?
So we're talking about like when you like suspend yourself or something, and like other processes send you wake up signal.
Okay, that's one thing. So when you suspend yourself, somebody can resume you. That's not really a signal because you're not doing anything. They're waking you up.
Right.
But in what does signaling mean in an operating system otherwise? So it's not resuming a process. I mean, that's just.
You have a mailbox, essentially, where you just occasionally check to see if there's something in the mailbox you need to look at.
Okay, that's a very good form of inter-process communication, which is what I'm going to use to unify everything we've studied so far. But that's not quite Unix. Okay, about occasionally checking. So in Unix, Rob isn't here. He would have answered this question well, but he knows that. Kill -9. Sorry.
Yeah, like kill.
So what is that? That's a signal going to that process, which cannot be postponed, and you don't occasionally check that. You interrupt that process right away. The basic model, that's how systems evolved, right? From hardware, they built abstractions that were further and further away from the hardware. And we had the kernel being interrupted by the hardware. And then they said, let the same kind of technology be used for the operating system to interrupt a process, saying, you're going to die. Do something. Enough. Okay? We'll send you the kill signal right now. And then they said, why should we just interrupt the process? Why can't one process signal another process? Okay? And in the hardware model, what is the hardware interrupt model? When an interrupt comes, when a device interrupts, and the device says, I have a new character. I have a new byte from the network. What does it exactly do to interrupt?
It latches onto a hook.
Sorry?
It latches onto a hook and then passes the information out.
And it passes it how? I mean, if I am a consumer of the character, being the kernel, how do I know a character got input? It puts that value somewhere in a stack, actually. And then it does what? When an interrupt occurs, the operating system kernel knows the interrupt occurred because, and it knows, how does it know that it was a character that was input rather than a byte from the network? Or something came from the disk?
Well, the interrupt would have some detail on that.
Some detail, so in the stack, it might go and say this kind of interrupt and so forth. But do you want all interrupts to go to, and then what happens after that? The kernel has to execute some code, right?
Yeah.
Which code in the kernel gets executed? Is there some well-defined code, one location that says whenever an interrupt occurs, execute this particular, jump to this address? All you guys who just did undergrad recently, what happened to all your 120 knowledge and your operating system knowledge?
So it's like I don't know, is it the system call call where
System call is made by the programmer. Okay, you say, I want to go and output. I want to do put C. I want to print a character. Okay, so it made a system call. The system goes and says, okay, I'll go and put that in some queue. And I'll get an interrupt from the consumer of the character saying, I'm ready to now get the next character. That is when I'll put it in a device register. Okay? That's what really happens. Or you say, I'm ready to get any input. And whenever new input is available from a device register, it comes to the operating system. So that's like shared memory. The value comes to the device register. It's there. But it has to go and tell the operating system it's there. And it does it by interrupting. It raises the interrupt flag. That interrupt flag is actually read by the CPU. And based on which device interrupted it, it goes and has to jump to some kernel routine. Do all the interrupts jump to one routine, or maybe there are different routines for different kinds of interrupts?
Well,
they're
there
different routines.
Yeah,
the question is whether they get called immediately or whether it has to go through some stage.
No, let's forget about it. They're called immediately. There's cycle stealing during, there's no such thing as interrupts. After every instruction, the CPU checks, is there an interrupt? Is there an interrupt? The question is, you're doing polling at that level, or you're doing polling at the browser level, Yeah.
Well, in terms of like reading from the hard drive reads to cache. The cache gets filled with the data, like we were explaining. It issues an interrupt to the kernel. The kernel then signals the process that was waiting for that device.
Yeah, but
saying,
but
you're
maybe.
not ready.
It's that step that we're interested in between it signals an interrupt and then it passes it to the process.
Yeah.
Like that part's the interesting bit.
That's the one we are talking about. Everything is, and that is the interrupt handler. Okay? Every type of interrupt has an interrupt handler. And the kernel, when it booted, said for this interrupt, there's something called the interrupt vector in low memory. It says, for every interrupt has a location in memory. And in that location, you put the address of the routine that you want the CPU to jump to when that interrupt occurs. And that can then pass it to a process or not. Kernel threads may or may not exist in the kernel. Okay? So, we will go and explain that to you in terms of software, which we all understand because we are not hardware guys. So there are and the same model is used in signals. Okay, or what I'm calling software interrupts, which is again not what Intel does. Okay? There's some things called traps, and Intel calls traps or software interrupts, which doesn't make sense to me. So I'm going to have a handler in a process, just as a kernel can have multiple handlers. And what I'm going to do is a form of registration. Okay, this is just like I should explain this in terms of the observer model. So you go and say, whenever interrupt number so-and-so occurs, please call this handler. You're telling the operating system this. Just as the operating system tells the kernel, the kernel tells the hardware that whenever this interrupt occurs, here is a handler. Okay? So that is your receiving process. The sending process will do what? The sender wants to send some information to this guy. He says, whenever this number interrupt occurs, I will go execute this code. So how do we communicate information to that? How does the sending process communicate information to the receiving process?
Sure, is an interrupt with that number.
Okay. Interrupt, process ID, because now we have more than one process that it could interrupt, and the interrupt number. And that's essentially what the hardware does, except there's only one process, which is the kernel. Okay. So here's the notification mechanism that we could use in conjunction with shared memory or alone to pass information. Okay. And why do you think OSs build the system? So now when you say interrupt this, and whenever that interrupt occurs, you go, when interrupt 1 occurs, you execute handler 1. Oh, I guess I'm giving the answer away. So, okay, no, actually I'm not giving the answer away. And this is very important. What happens when an interrupt occurs? You are merely executing code. And actually, when an interrupt occurs, who's the you? Well, the kernel is executing code, right? Ultimately, it is some process, some user process that's executing code. It's got a stack. And suddenly an interrupt comes right on top of the stack and says, I'm going somewhere else. It services the interrupt and restores the stack. No ceremony here. No, are you fine? Can I do it? Absolutely not. I'm doing it. That's interrupt. That's somebody coming into my class and says, I don't care what you're teaching. Here's a fire problem or whatever, and everything. So some emergency. Okay. And why so this could be used for inter-process communication. And it was not quite designed for it. It was designed first for something else. And why we know why the hardware might want to interrupt the kernel, right? I mean, the hardware's got a new character, the hardware wants to consume a new character, is ready for a new character, so it does that. Why might a process be interrupted? I mean, why did this idea first come about? Think of the example I just gave. What is kill really? Kill is sending signal number 9, that's in Unix at least.
Well, the only thing I can think of is that you want to prioritize certain things over others.
Well, you want to know if something is changing, like the assumptions you've made. So, like if you're operating under the assumption that, oh, I'm going to be running in a minute, or I'll be like the computer will be on in a minute's time, and that state's about to change. You want to know about it so that maybe you can quit cleanly. So,
maybe the power is going to go down. That's an interrupt that really occurs. Right? I told you guys a joke about IBM versus DEC. You guys don't remember?
Oh, I think you told us.
Yeah.
I don't remember what it was.
Anybody remember?
Oh yeah, they wrote like the accounting information, like when it died, none of the other stuff.
IBM wrote the and DEC saved your files. That was a DEC joke, right? So
Actually, it happens when you run out of memory too. I've actually had that happen. I forgot to set up swap on my Linux computer, and then I write over it, and just everything's because it'll just randomly go process until it has more memory, and then it's
yeah, so that's the analogy I had was that there's a fire, interrupt, right? So
I think it's right, but I don't remember exactly. Sometimes they'll just use the one with the biggest memory, which seems like the more usable choice. Sometimes it's not very stable at that point.
So yeah, and by the way, a new thread is not created for this. That's a very important point. You own the current stack, you just accumulate these things. Okay, so if an interrupt, and it's a real mess when interrupts interrupt other interrupts.
So
And in fact, in the hardware, we make sure that interrupts don't interrupt other interrupts.
if you signal an interrupt in software, does it immediately perform does it write the memory that it needs to and then immediately perform a context switch?
So then it will. So that the interrupted process might or might not be executing, right? And it's a design issue whether you go and make it execute, get the CPU right now, or next time it executes, you go and I actually don't know whether Unix goes one way or the other. The idea is that next time it executes, at least by that time, it shouldn't do more work.
Right.
So the fire analogy is probably not right. Basically, don't say another word till I've told you about this event. Okay, and so yeah, right. That saving files one was actually between the hardware and the kernel. In the kernel, of course, it goes immediately. But when it's between processes, then we're not talking saving files. We're just saying clean up your state or whatever. And if you're Microsoft Word, save your file. Okay. So the new thread is not created. Use a stack of the current thread. Okay. And it's really meant for OS process communication. When you say Control-C, an interrupt goes to that process. Okay. And I was telling you how Eclipse cannot send, I don't know why, yeah, I guess that's it. That in Eclipse you can't send that signal, but from the OS. Some alarm set by the process has gone on. Some limits such as file size or virtual time or virtual memory is expired. Okay. So you guys like this model for just inter-process communication? Why?
This is dirty.
What's dirty?
It's not gentle.
So in what sense? Yeah, let's dive down into that.
So if I'm trying to do some bidirectional communication in processes using these, I'm going to run into trouble, particularly if I'm writing to a process, which means I'm essentially constructing an interrupt to that process. And then in the process of doing that, I'm interrupted because it's got some data that it wants to give me. It takes the control away from, like, I had some processing that I needed to do before I talk to you next. But you're forcing me to talk to you, or at least listen to you via these interrupts.
Okay, so there are ways to disable interrupts and enable interrupts. So imagine you can do that, let's say, okay, right now, I'm just, yeah, but you're right, you can't really, and what happens to the cumulative, basically you will lose the interrupt, or you can only have one pending interrupt at one time. But absolutely, you have to, there is no, with shared memory, the problem was that you might not know something got changed. You can't, and so you might delay things. Here, the way I've described it to you, you can't delay. You must service it. Everything is urgent. And how much information are you conveying to the other process?
Very little. I mean, you can't really send specific messages or an object, right?
Just say interrupt number 1, number 2, number 3, number 4.
It's like this happened.
Just one word of information. Not even,
I mean, I guess you could do some trickery with some shared memory.
Yeah, so you can use it in conjunction with shared memory.
Yeah.
Absolutely, absolutely. That was the point, yeah. Okay? So, familiar interrupt model for IPC. When I say familiar, I thought I was, so how many, we just figured out that you guys weren't familiar with the interrupt model, right? So, this familiar interrupt model. And I'll tell you guys, I mean, I thought I was fantastic with operating system when I was a grad student. I mean, I aced the PhD exam. I actually built an interrupt handler, okay? And I thought I was licensed to go and teach operating systems. And to be honest, I didn't know how interrupts worked. I had taken the interrupt handler for one machine, morphed it to make it work for another one, just as you guys take the RMI application from one place and you made it work for yours without really understanding all the theory. And I never knew why certain things were happening. I mean, even went to my advisor and said, why am I doing this? And he said, this is frobbing. I don't know what frobbing meant, And then I read Doug Comer's book on Xeno, which really talked about interrupts properly. That's when I understood it. And again, I'll say those who can teach, not those who can't. Because, when you teach it, you really understand it. So I had only when I was a professor teaching operating systems that I really understood the interrupts, how it really worked. The details, there's so many details, that I haven't told you about. And Kevin always laughs that the first PhD student was one of his best students, Don Stone. He did a PhD on operating systems, but he was mortified of the idea of writing an interrupt handler. Okay, so yes, it's messy, it's not so familiar, but for anybody, but it's existing model, okay? And it's something we teach our undergrads, right? In what was 120 and now is what, 520?
530.
530? I mean, assume you guys study that stuff, right? So, but you do, or I mean, really, you do or you don't? You guys, I mean, or is it very covered, very...
No, you do interrupts for solid 2 lectures.
Okay.
It was just a long time ago.
Yeah, sure. It's a long time for you. Just imagine, So there's no parameters of the event. And, we're assuming, at least the way I've described it, we're just assuming basically one. But it's nice to at least understand this coupling. You really put things in context. Right? So receiver cannot delay processing information. And yes, there is a way to sort of put interrupt masks saying I'm not willing to receive these interrupts. And then there's a big issue of what happens to the signals. And if there are 2 signals, what happens to them? Do they get queued up? And they don't. Okay? So that's the challenge. Okay? So we're going to call everything that is not interrupts and shared memory as message passing. That is the world that we have seen so far. And we'll have to figure out what exactly it is that unites them. We know they're different. We know that these systems are different from, these shared memory models, if you will. And I'm going to consider RPC also as message passing. Okay, and we'll try to just be very general about this model. I do want this big design space where everything we've covered so far, to some degree, is points in that design space. Okay? So we're going to try to figure out the common mechanism and issues. Okay? And I keep talking about the system Gypsy, and I called it generalized IPC because I was trying to do this very general model where all of these things were special points so that you could take one system, and even if the system is a totally useless system, at least you can go at an implementation level, see the differences between various points it does support, which may be the interesting things to use. Okay? So now tell me, what is something that we're going to see how these guys are different? You know, there are a lot of ways in which they're different. In what way are they similar to each other? And that similarity should really distinguish them from, you know, what we've seen already. And that similarity clearly has to do with the word message. So what's a message passing system?
Isn't it just the fact that you can send parameters in the event? It's also something you can't do with the other things, right?
So it is something where you send some piece of information.
Right. Something about the event that happened, not just that it actually happened, something about it.
Some information.
Right.
Event, data,
Yeah.
you know, whatever. And what is the word that you use that I said defer it to later? When you said an interrupt is really a mailbox. So you're sending to who? You're sending to a particular process? Or you're sending it to maybe a mailbox? And then a binding occurs between a process and a mailbox.
So there's not just the one mailbox, right? I mean, I guess you could and like reroute.
So you could have multiple message mailboxes, but remember when I send a message on a socket, anybody listening to the socket will get that message. And you can have multiple processes reading from a socket and reading from a pipe. That's why I said it's not a process that you're sending to. You're sending it to a mailbox. Now we can decide who sends information to this mailbox, who receives it from the mailbox. We can talk of various variations that will tell us, let us distinguish among these. Okay? So here's a picture. It says almost nothing. But it does say mailbox. You don't know what quite mailbox is, but it's something where you can queue up. It's a queuing point of messages, some blob, object. We'll try to figure out what that blob is, how it's structured later. It's some blob of information. And there is a sender. There's a send operation on this in terms of an object. There's got a send operation, and there's some way to communicate information to a receiver. So there's some way to deposit that message to the mailbox, and some way for a receiver to get. That's my message pass. So what have I not said? Like I said, almost everything. But what are some of the things I have not said?
Like, how do we let the process know something's waiting in the mailbox? Does it have a poll? Do we send it a signal?
Okay, so what's the exact operation to go and put information in and to get information? Okay, what else am I missing here?
This maintenance of the message.
What's the content? What's the side effect of sending? What's the side effect of receiving, if any? How did you get a connection in the first place? Okay. Can you send back information?
Well, the other process would have help.
Maybe, or maybe you have a reply. Maybe you have a reply thing where you can just. How many people how many people can send to a mailbox? Maybe only one. Maybe multiple. How many can receive? How many people, meaning processes? How many can receive? Maybe only one. Maybe multiple. And why? You know, I mean, there are all these things. Anything else? Does everything I send get through?
Well, that right. You need possibly a bounding size.
Some bounding size. How many? You know what happens? Okay. And we've seen all these variations, right? We saw Xenu. We saw various design. So let's look at anything else that comes. If I'm teaching IPC, you know, there's one. The most fundamental issue people consider is has to do with blocking and not blocking semantics, synchronization, okay, which is kind of, how do message distribution. So let's go and see. So the common basis is processes, threads send each other messages. Sender deposits messages in port queue of varying size. Who knows? We're not saying anything about the size here. Receiver gets message from the queue. Okay, and I'm all doing it through diagrams because I don't want to say very much at this point. And what are these? And I could have gone to those points and said, okay, let's go and see what the differences are. But is it reliable or not reliable? Which is really a networking issue. But is it in order? And port access, meaning who can send, who can receive. And I'm going to also say routing, by which I just added this yesterday, and we'll see whether it makes conceptual sense or not. The other stuff I've been teaching for years, so I think it's more debugged. But this stuff we'll see whether it makes sense. But I just added some more things. That where's the message going? I mean, to who and to how many people? Yeah. What are the semantics of send and receive? I haven't even said that. Which means what are the operations? Is it synchronous? Is it asynchronous? What does synchronous, asynchronous really mean? Especially because there's also blocking versus non-blocking. And maybe those are different concepts from synchronous versus asynchronous. Okay? And, there's queue size issues. Is there buffering? No buffering. So we'll go and yeah, I'm not sure what I mean here. Okay, good. I suppose they could be on the same computer or a different computer, but I don't know what else I mean here. Okay, reliable versus unreliable. Let's quickly go through this. This is really what the networking guys talk a lot about, but we'll at least talk from an application point of view here. So reliable, every message sent to a port is receivable. So given that there is a way to get reliable communication, why do we ever go for unreliable?
Sometimes it's faster.
Yeah, that's true.
I told you guys that when I had to do my demos, I just changed TCP to UDP, and they went much faster. Right? But there I was doing a demo, right? I said if nothing bad's going to happen. Are there real applications that can afford such unreliability?
Streaming video, like if you lose a few pixels.
Sorry?
Streaming video, like if you lose a few pixels, you could still
If you're sending a video of me, you miss every alternate image. Are you going to really lose anything? Yeah, you might gain actually. So exactly. So that's why it might be useful. And what's the cost of reliability? I mean, yeah, fine. Some applications can take. Fine, we know that they can be. There's unreliability. Okay, so I didn't answer that question. Why might things not reach?
The mailbox is full. You can't stuff it.
Okay, so maybe the buffer gets full.
Maybe the process that has the mailbox is closed.
So maybe the
Shut
process.
down and it's-
Somebody died. So then, if somebody died, then if somebody died, then should we even send the message? I mean.
Well,
But yeah, why is what's the classic reason for messages to be dropped? Maybe the buffer at my computer is full, or the buffer at, okay, or maybe just some signal noise, lightning striking. Who knows? Okay. So okay, we can all go and do retransmissions and make sure that message eventually gets through if the process is if there's a route to get there. And so why don't we always want to do that? Even though there are some applications, video streaming, where we don't need reliability, why not just send messages?
Because by doing that, you've made it more likely that other messages will fail, including your own.
Okay, because
So if you're like we use the networking example, if the reason your message got dropped was because the queue is congested, the solution to that problem is not to then send a lot more messages.
yeah, the solution is not to send more messages. But you know what TCP/IP does in that case?
It slows itself down. So it speeds up until it drops one, and then it just cuts the sending rate in half.
Yeah, which is pretty drastic, right?
Yeah.
So that'll
increase what the-
that'll work. But still, you just don't want TCP/IP sometimes because is TCP/IP slower or faster than UDP? It can't be faster.
It's slower.
It's slower.
It's an overhead, right?
But there's the problem with good put. Sometimes you can get
More good put through
data through with TCP.
because there's back off.
Yeah.
Okay. So anyway, when reliability needed, programmer does not need to implement it. And spam load averages. I'm setting my load average. I'm doing some kind of distribution, so I'm just sending a load average. And every now and then you miss it, big deal. You'll get it eventually. Right? Telepointers, you're moving the telepointer, and it doesn't move, that fast. It's okay. Our eyes can only track so quickly. I've tried actually. If I go and just send a telepointer, it goes every 1/10 of a millisecond. Every 10 milliseconds it goes. The INTRA goes. And we don't need anything as fast as that. We can slow it down to 30 milliseconds or even 100 milliseconds. Okay? So you can generate a lot of events, by the way. Through a telepointer, you can generate very fast traffic. It's almost like video. It's more than video. Video is they're generated at a certain rate. So reliability is less space efficient and time efficient. Okay? Because you've got the algorithm, you've got to send extra information, so maybe you don't want it. Okay? But anyway, we are not going to go deep into this because networking guys, that's what we'll talk about. In order, not in order. Okay? And again, are there applications where we can afford not in order?
Well, there are always ways of saying that I'm okay with receiving the message out of order. I'll reorder it myself.
Okay, but then that's, yeah. Then you're doing, you might as well get from the system. They'll probably do a better job.
That's what I think Netflix does a bit of that, where if they get something out of order,
Okay.
it has a little buffer that it can swap between. But
Yeah, I was gonna say something. Hey, if you're thinking of like torrents or something, it's like, okay, I don't really care.
yeah,
As long as I get
yeah, that's true. If I'm just trying to, like, with BitTorrent's a good example. If I get something out of order, that's fine. I'll just put it where it goes.
Okay, so basically the operations commute.
Yeah.
Okay. So, and why might this happen? So commuting operations. So you don't have to send sequence numbers, you don't have to do a lot of stuff if you want to. Okay, networking issue. Just to sort of put it in context. Okay. So, mailbox. Okay, who's supposed to be, if you take the physical mailbox analogy, anybody living in that house should be able to access the mailbox, and anybody else who does it is a crime. Right? And only the postman can put it in, but effectively anybody's putting, so postman puts in. So there's all these access issues. So the question is, what are the sets of senders and receivers of a message? That is the question I'm going to try to answer. Okay? And the answer is simplex bound port. Okay, and we'll try to build from this. Where you have one sender who's only sending, you have one receiver who only receives, doesn't send back. Okay, that's it.
They share mailbox?
Sorry?
They just share
No,
mailbox.
because
It's one
it's unidirectional simplex.
Oh, right. Okay.
Okay. That's the simplest thing I can build. Is that a square wheel? Or are there any applications that could ever use this? You have more guarantees, by the way. Huh? You didn't want this global variable? I'm going the other extreme now. I say, this process sends and this process receives, and you can write all the assertions and you can prove your program is correct, even though that program is a useless program, right? So can we have a useful program where we can do all these assertions, can prove all these assertions?
I mean, are we allowed to duplicate it and give us duplex?
Okay, so if you're going to duplicate it, you might as well have one channel where you send it back also, right? Is there any situation in which somebody just sends data? Yeah.
GPS.
Okay. So the GPS data is just going. Okay, and you guys are the new generation.
Don't send anything to the satellite. Your GPS receiver
Just
only
receives
receives.
Only receives, right? So that's what I meant. Yeah. And so that's okay. So that's a good answer. And way back, any other examples?
Pager.
Okay. All these modern examples. We're going to look at my example and say how boring. Well,
You're being sarcastic.
No, actually, I was not being sarcastic. This stuff got invented when file systems got invented, okay? So that was the canonical example, that you're sending a file, which is, in some sense, it encompasses both of them. You're sending a file of data. You're sending some stream of data where one is the producer, one is the consumer. And you just, but that's what people said. We can have a simplex port like that. And now duplex. So what can you do with duplex that you couldn't do with simplex? Some interesting application? You were thinking of some application where you wanted 2 simplex ports?
Well, yeah, so now you're okay to do something like the web.
Yes.
You make a request for some information, they read that request, send the response back to the mailbox, you review it.
But the thing is that, how many senders and receivers are there?
Well, in a modern one, many.
But even an ancient one, never was there. Never did one client have one web server. You're saying that this.
Oh, this is what I think I see. This is the token ring.
So what I'm saying is that yes, you're going to get to what I'm going to talk about next. But this is a duplex port. 2 parties involved, and only those 2 parties. Whereas with the web, we have one web server being servicing multiple targets.
Oh, I see what you mean. Okay. So.
Maybe this is not a very useful abstraction.
Maybe something like a security scan or something to get into a door.
Okay.
Like some central security system is talking only to that and is saying.
My office, just me.
Yeah, exactly. Send me the data from his thumb print, and I will check to see if it's okay, and then I'll send the okay to unlock or not.
Right. So it gets a result back, and maybe it just listens to one guy. By profession. These are very restrictive ones, and I don't know why I have HTTP connection, but that it doesn't work fine. But some kind of 2-player game, if there is, you can imagine that. Okay, but HTTP connection is really not the right. Oh, what I'm saying, I guess, is that once you've gone and contacted a server, you might get a connection. That's just between you and that party.
Yeah, that's what I was thinking.
Okay. Okay. Yeah.
Connection.
Yeah.
We were restricting it to where one machine was only allowed to ever have one of these things.
No. They can have multiple of these. So you have to first go to the socket. In fact, when you think of your socket, a socket takes 2 forms, right? One is the form where you go and accept on the socket, and then when you accept, you get a new copy of that socket, which is a dedicated connection between 2 parties. Of course, multiple people can receive and send on that, but typically it's 2 processes. Okay? A pipe is typically between 2 processes, though you can have multiple processes. Okay, so it's not such a great idea. But of course, greater than 1 sender receiver, and that is where we'll go to what we'll call an input port. Okay, it has multiple inputs. It has multiple single input, and if you will, multiple outputs. Okay? So you can call anything input or output, but that's just it's got multiple senders and 1 receiver.
But does that model fit because the server is not able to actually serve anything in this example?
Okay, so is it ever useful to do this?
I mean, like if you're observing the stock market, you want to receive
Some sort of like multi.
Yeah, like you're wanting to receive information from a bunch of different data feeds, but you're not interested in sending anything back.
You're just
like
collecting
like instruments or something. You're just like checking measurements. Or something.
Yeah, sensor, all these sensor systems. They're just getting sensor from, again, modern example, right? So this is very important. This is not multiple simplex ports. These messages all get queued up in one place. And if you're collecting sensor data, yes, you want to know the order of the various measurements. And you don't want to have separate queue and then have to go and say, okay, this because you do want to see, the correlation between these. Okay? So that's important. It's not just a replicated queues.
In this case, well, the mailbox do some floating.
Sorry?
In this case, with multiple lines, well, the mailbox do some floating job like the actual mailbox does on the server.
Server will do. Mailbox is just this mailbox. Server will go and say, yeah, I like this message, I don't like this message. Okay? And again, guys, I'm going to go back to the ancient examples. So, the print server is an example of this, that you just have multiple lines. Okay? And where am I going next? So few examples where no information comes back from the server, okay, which is kind of what we will see. But again, sensor data, printing, they're all good examples. And what would a duplex port semantics really mean? Let's try to figure that out. That's it.
I expected this part, but is there a sense in which you can truly reply? I mean, does it go to everyone, or does it just go to a specific client?
Okay, so let's think about that. So how would you define this? I've got these arrows, and I've got, I'm giving you a little hint. So, and think of reality.
Right.
Okay, think of a web server saying, you're going and it's displaying pages. So when the server replies, clearly the reply goes to one person, goes to the person sending, right? And what would duplex mean then? So clients deposits message in the mailbox. This way the messages are going to this. When information goes back here as a reply, we know it's going back to the guy who sent it. And beyond that, could it mean something also? Because, this is the question. Reply, the semantics are clear. Could we extend that semantics to allow server to contact clients, so that send messages to clients that are not replies?
Sure, you can have a broadcast where you say both clients are reading the entirety of the mailbox. You can both get all messages.
So you could, a relaying server, which is what you're thinking. I send a message to this guy sends a message to everybody else. And each one of them is a separate connection. There's no common mailbox there.
Well, you could have, you could architect out a game so that each client is sending their actions to the server, and the server is just storing the current state of the game in the mailbox for both clients to get simultaneously.
Okay, again, this mailbox is operating the system-oriented thing. So there's no application-specific functionality here. It's got its own little buffers, From your mailbox, things went into your desk. And that's when you go and unclutter things. Okay? So this guy could go and send back messages. So we'll define this as, it's a like simplex equivalent, except that the server can send messages to clients, and each client has a separate queue. So we are not talking of a common queue there. Right? And when you allow this reply operation, then the send becomes just implicit. Whosever's message I'm right now processing gets back that result. And how is that decided is a little tricky. In a remote procedure call, that's easy. If it's not a remote procedure call, it's a very tricky issue. What does that really mean? Okay? But assuming that can be decided, I can have a reply. Okay? Okay, so what I'm saying is that in replying port, the replying port is a narrower form of duplex port, where you can only send back information to the one who sent you. You can't just go and say, I want to send message to this particular party. So I can't build that relaying service. And why would you, and I'm saying, having a replying duplex port rather than a general duplex port is got a simpler API, because you don't have to go and name anybody. You just say reply. And I says from security point of view, this is useful. Why from security? And this is really important. You go to an organization, they really care about this.
Well, since in this case the server is going to be replying, it's going to be replying only to that person. So it's
but even in my general thing, okay, so it's not sending messages to everybody else.
right. It's not going to be. Client 1 can't see what client 2 is doing.
So in some sense, that's okay. Other reasons? The client will receive message only at certain times, right? Only when it sent a request. That means it can never receive message otherwise.
Well, it lets you, this sort of conforms to firewalls and this sort of thing, so that I don't want to allow traffic into my network unless I ask for it.
Exactly. Okay, that's what they want in Microsoft. They want the computer on your desk to only receive information when it asks for it and have no denial of service attacks, which Microsoft is a good target for. Right? Okay, I know we have to hurry because, so we'll just stop at this point. Carry on from here next. We have to hurry because Justline's course takes over very quickly. And we were abstracting. Okay, it's not as if the stuff you've learned before can't be, there's not enough interesting questions there. Okay, but we were abstracting and saying that let's not look at these points in IPC, let's go and look at design space, so that we understand things at a more conceptual level. Maybe we can design something more grand also. Okay? And we saw that in message passing, we saw IPC consists of software interrupts, shared memory, and message passing. Okay, so we are diving deep into message passing, having seen the problems with message shared memory and software interrupts. Okay. And we said, okay, what is message passing? Well, it's a very broad topic, but the whole idea is that there is something produced by a sending process and something consumed by a consuming process, and these things get queued up. Okay, and they get queued up in a mailbox. And the sender produces into the mailbox, and the receiver consumes from the mailbox. That was our basic thing. And we said, let's forget about the nature of messages for now, and let's just see that given something has been produced, who can consume it, and how many producers and consumers are there for a mailbox. So basically, access and routing issues. Okay. And we saw that we could have two parties involved. And if there are two parties involved, we could have a simplex or a duplex variation. And here's a duplex variation. Okay. So just two parties involved. Okay. And sometimes that's interesting. And we saw all the scenarios. And then we said, okay, when there are multiple parties involved, we might have not a bound port, but an input port, where there are multiple producers and a single consumer. Okay. And we saw there were many examples of that. Our file server, HTTP server, there are multiple clients trying to open a file, and there's one file server that's got the file. Okay, and that's a duplex case. If it's a simplex port, then we said there's a print server, and there could be one print server being shared by multiple clients. Okay, so these producers are basically clients. The consumer is a server, and we typically expect one server with multiple clients. And we saw there was replying duplex port and a general duplex port. Replying port meant that the server could only send back data to the one in reaction to a message. Okay? Whereas in the arbitrary one, the server could go and just send things at arbitrary times. So if you want to do your relaying server, okay, I need to get a message even when I haven't requested one. So I need something more general. I need the duplex one. But if you're doing web searches, searching on the web, then you send a query and I can give you back the answer. You're not getting answers unilaterally. Okay? And again, security-wise, the replying one is safer because a client behind a firewall cannot get denial of service. You can't just send it a whole bunch of messages it doesn't expect, and you can't flood the traffic. Okay? So that was my input port. And now, of course, we are mathematicians, we are theoreticians. So if you have input port, the dual would be output port, which would be this picture. Okay, so when we put a theoretical hat on, we get this picture. One client sending messages that are consumed by multiple servers. Okay, so what would the semantics be? If I send a message, the message goes to which server?
You can put it in the header that this message goes to this server.
Okay, if I'm putting it in the header, then I might as well have a separate duplex port with each one of them.
You could just send it to some central mailbox, like send it to some network storage, and then the servers pull it every so often, or the box notifies them that there's a message pending, and they retrieve it.
So each message is retrieved by how many servers?
One.
People get very confused.
The MQ, like an MQ server.
So what's an MQ server?
Oh, so like you're thinking of like DUPLEX or something like that? Where
Yeah, like
you can have like multiple workers.
you know,
there.
like a file. You have a file, but when you get like you want all these guarantees and stuff, you get a database. Well, if you have like a queue, when you want like a nice like queue where the guarantees and a message will only be read once, nothing will be lost, all that stuff, you get an MQ server. And there's like a whole bunch of different implementations, but when we would do like loan processing, this finance company where I work for, you would fill out something online, and it would send like this data packet to an MQ server. And it would just sit there like if the servers went down, the processing servers went down, you would be guaranteed to have it in the MQ server, and only one would get pulled. And if it like got pulled and something happened, it was like these transactions semantics were really cool. Like made writing software a lot easier. It did all the thinking for you.
Okay, so the broad idea that there's a queue shared by multiple servers is the main thing. This is not broadcast.
Right.
Okay, we'll get to broadcast semantics also, whatever that means. The idea is that there is one mailbox and multiple consumers. Okay, so somebody's sending you a lot of letters, and multiple people from your house are consuming the letters, and sometimes I get the message, sometimes you get the message.
Would this be used by replicated servers? Suppose it's two servers who replicas of replicates, like maybe Gmail server. Like I'm sending an email, it could be consumed by any one of the numerous Gmail servers that possibly exist.
But then is it replicated? It is partitioned.
Exactly. So would this which is what the question that I'm asking is this an accurate model of what happens with replicated servers?
No, for that you need broadcast of some kind.
Which means that if I send an email through Gmail, it gets broadcasted to every
At some point, either I send it to one server, which goes and sends it to other servers, or logically.
Yeah, but what that server will, if that server chooses to broadcast it to other servers, that's a call that server will be. But this.
Yeah, if it's sending it to one server only, then when was the server bound? At sending time or at, the question is there a shared queue or not, is the issue. Otherwise, I can just have a little bound port. I send it to that server, the server sends it to other people, and I just think there's a bound port. So the question again is, am I addressing that server? When I send the message, did I know which server is going to go to? Or is it going to be, whoever goes and picks up first?
Where does the mailbox reside?
So that's a good question.
That's what I was thinking. Like, if we know which server we're sending it to, but what if that server is our mailbox?
Yeah.
So that's an excellent question. And let's just postpone that a little bit. But what do you think? What do you think? I mean, how many machines are here? 3 machines. Which machine do you think should reside on?
And a separate one. So that's the
I'm with
easiest.
this guy, yeah.
Just have another machine, mailbox machine.
You need to have like.
Wait a minute, guys. Wait a minute.
Alternatively,
How many senders are there?
No, there's one sender, so you put the mailbox in the sender, and then you notify the servers that you have a message.
Otherwise, you have a message going.
That's not very scalable. Like, this is of course SIMPLEX output port, but what if you had like.
Okay, no, let's. That's why I was going to postpone the discussion a little bit.
In the most general sense.
No, but this is output port. This is output port. Simplex or duplex doesn't matter. When we go to something called a free port, then your issue becomes a very good issue. Okay? But right now I'm saying, I'm just putting my theoretical hat on, and maybe it's a practical hat also. Where I said, if I certainly one server, multiple clients is a very practical situation, right? I'm saying the dual of that is one client and multiple servers. Okay? And then the mailbox goes in this guy's machine. That's the queuing point. And in the case of input port, the mailbox went into the receiving unique receiver. Right? So that's an excellent question. And the question is, where is this useful now? I know you gave an example, but you didn't give me the full thing. You said that's something. So yeah, you were going to
something that
one sender. Remember, one sender.
Yeah. So something I've seen is that if you've got like say a web server, right, and you like dispatch like lots of like cron jobs or otherwise difficult computationally intensive tasks, then you can send it to some like message queue, and then the like worker threads can pull from that message queue.
Absolutely.
And you have sort of synchronized.
That's a basic idea. That you go into a barber shop and there are multiple barbers there, and whoever's free next serves you.
It's sort of like I've seen Blender rendering farms that operate on this, where you send a job to like a central pool, and then whichever rack server happens to be free at that point grabs it, does the processing render for you, sends you the picture back.
Okay,
That's
so that's
not a correct example. Because you can have multiple clients and into a single vendor server.
so that's the question. Did you have multiple in
No,
yours?
no, but I bought one. I bought the pool. I bought this farm for myself,
Oh,
and
so
then
that
I
farm completely belongs to you.
Yes, I bought it. I spent lots of money.
Then it's okay.
Okay, but that example is still, come on, put your exam hats on. Simplex.
I know. Technically, I'm getting the message back at some point,
Yes.
but
Yes.
That's true.
Okay, in your case, his objection holds true.
That's true.
Because
You need some sort of result.
the clients, no.
Well,
There are multiple clients to your web server. He's saying he's a pampered client.
right.
He alone has 5 hours saying, me,
So I understand that, like, because I'm getting some sort of reply, then that obviously.
So that's one issue.
It's not this, but
But also, how many situations are there where one pampered client has multiple servers in practical systems?
Over the years, software updates.
I mean, I can only think of like a
Absolutely.
sensor
But
network.
yeah. So software updates where you're just distributing something. Sensor data could also be like that.
Yeah.
That you've got,
just saying, hey,
we all want to know what's happening in Mars.
You can send like a command, right? So that, say, I want to launch a missile at Congress, and I just send it to a central queue, which then says whichever missile silo is within range of Congress, just go ahead and send that missile out. I don't need any feedback from you. Just blow them up.
No, the
Practical. I was looking for a practical scenario, and you'll just blow up the world, and so practical won't matter.
software updates don't work for software
Yeah,
updates message.
it's a broadcast. It's a broadcast. Sorry. Yeah. So, arbitrary number of receivers called servers sharing a single queue, not broadcast. Message goes to a single server. It is not broadcast. Example, you're distributing some coupons. Sort of an example I could come up with. So each person can get only one coupon, and whoever the first 100 people who are consuming, they get it. Okay? So, but now we get to the duplex case, and server can send message back to client. Example, and you are so pampered, you're so important. You're trying to find the meaning of life, perhaps, or maybe life in another planet, life in other places. So maybe you just have this, whichever the next server goes and does the next part of the computation here.
That's interesting. Because in that scenario, our laptops that we've linked onto the setting would be the servers, and the client would be whatever data collection rig settings using.
So this is always a confusing thing. We always think what's on our computer is the client, and what is far away is the server. And where you guys, maybe Rob would know this. Anybody heard of X? Windows system?
Oh, God.
Yes.
They have it
Oh,
totally
God.
backwards.
That is
Totally
the
backwards.
most
It is
convoluted-
perfect. Why is it backwards?
Because the X server, in their point of view, is the thing with the keyboard and the monitor, because that's the thing sending the messages.
No. I'm sorry. That's the whole point. What is on your computer and what is a server are orthogonal things. They are beautiful because the client is running on another machine. No. The client is running on another machine. It needs a server that will display its data. It's semantic. It wants a display server. It wants an input server. So it says, okay, you can be the server or you can be the server. It needs the service. Your display is just a service. It's not dependent on that
I know,
client.
but whenever you're talking to somebody and it's like, yeah, my X11 client's all busted, it's like, wait a minute. Are you talking about the thing on your laptop, which is the X server, or are you talking about the thing on the machine, which is the actual
I know.
client? It's
People don't think orthogonally.
that's true.
And if you thought orthogonally, exactly what we saw with it, that the faraway machine is the client and your computer is the server. Why not? You can provide service
I
too.
know, but it just annoys me to death every time you have to troubleshoot something.
Okay.
Troubleshooting isn't a bad thing. Trying to explain to other people what you're troubleshooting.
Yeah, when you're trying to get the, what's broken.
I don't even answer what you want.
I promise you don't want me to answer that question.
Okay. So this is your duplex output port. And again, we don't quite like this. I don't think it's ever been implemented. Few examples, but this is where you guys were going. Okay? That multiple clients, multiple servers, this is what you guys were going for. I mean, this is what you wanted.
Oh, yeah, but I like being responsive back.
Yeah. Well, okay. Now, hang on. Is this useful?
Yeah, of course it is.
Example? You guys gave lots of examples. I mean,
Yeah, so the Gmail example, if I want to get this message available to all
broadcast versus.
Oh, God, thank you.
Again, this is not broadcast. This is the joy. This is the joy of thinking. But,
Wait, why would that be broadcast? I'm still confused.
No, I understand what your confusion is. You're thinking that, like,
It goes to every single replicated Gmail server. So each one of them sends an email.
or it's partitioned. It's either partitioned or it's broadcast. If it's partitioned, then when I'm in India, it goes to my Indian guy. When I'm in America, it goes to this thing. And then, of course, when I come here, what's going to happen? So it's not partitioned. And every now and then, by the way, if I do log in from an Indian browser, or if I remote desktop from here and log in, I'll get consistent data. So I think it's synchronized pretty frequently. It's not like end of the days kind of thing.
I think the picture you were talking about is that picture, but then there's more below it with linking all of the servers together. So like each server does processing on the message that you're sending it, and then after the processing's done, synchronizes some state.
Yeah, but again, remember, a collection of input ports does not make a free port.
Right.
And if those messages have to be in a single queue, then it's this picture.
Can we go back to
We'll lose the recording. Just use your imagination a little bit.
Alright. The thing is, I'm thinking about the case where you have like the license server, which has a limited number of floating like licenses that it
What server?
license server, like MATLAB, for instance. Like lots of people in my network are using MATLAB, but there's only like 100 licenses.
Ah.
So which would that be? Would that be the duplex, or would that be this?
No, that's like a coupon distribution, no? That's like
Not coupon, but the licenses need to be returned with MATLAB.
Okay, then that's duplex. Yeah, simplex is a very boring one. It's seldom a useful thing. Sometimes it is. Most often you need.
That would be duplex.
That would be
Which
duplex.
means that, but it would essentially be equivalent to the clients putting messages back into the mailbox.
No, so the reply is always sent back in a separate channel. The replies don't go back through the queue. Absolutely not.
So the replies don't go back.
No.
That's it.
No.
This could be something. No, that doesn't work because then you need to synchronize. Dang it.
But, so free just means it does.
No access control. No access control. Multiple clients, multiple servers. That's what free means. Okay, so do I say here? Arbitrary number of senders call clients to a single message queue. Arbitrary number of receivers, typically called servers, showing a single queue. Examples? We saw a variation of this example. So firstly, if people are just sharing information about, so actually, that is, the load distribution is more a broadcast example, I think.
No, actually, that's pretty accurate.
It works. It's just assuming you never get a reply back from any of your servers.
No, what happens is each client queues up and says, I need a server, I need access to something, and then the server says, I'm free, you can come on to me, and then the channel is established elsewhere.
Well, so you just queue this, and then your
It's a
actual
request.
communication happens
It's a
outbound
yeah.
with this?
Yeah,
It's a
Okay.
request.
the initial request I think goes through the load balancer, but then once you're on a server with a session,
Yeah, that's
you need to
absolutely
stay on that. So yeah.
Yeah, well, but the thing is that, we are not putting too many smarts here.
That's exactly, how smart can the mailbox?
The mailboxes, so this is not a good example, but a shared pool of print servers.
There we go. That works. Only because your response is done by physically walking over to not response.
Well, mailbox.
Wait a minute.
Wait, why would someone do that? Which means that there's some printer somewhere, and I don't know. That would be horrible.
Oh God, you're right.
No. Why are you assuming that all the print machines are not in one room?
If they are in one room, I have to physically go and check every single printer which one my document was sent to because I have no control over it.
Yeah,
That would be horrible. That's evil. Why would someone?
So here's the situation, guys. You guys haven't published enough. I tell you these deadlines. having, 8 o'clock. It's always, I told you guys, Hawaii time is chosen as the latest time. And, often what they do is they say, okay, just print it in our machine so that we don't have to wait, So I guess this is, you guys actually, this is all this electronic submission. So at one time, you had to go and send physical copies of papers to it. Okay, this is not going to gel right now. And we used to FedEx our papers. Okay, so the issue was that, when is the FedEx guy going to come? When is the latest point? And the guy comes here or the guy goes to Kinko's, and we all knew that at the airport was the last point, so we would all drive and put our papers there. And then people got smart and said, let me go and print it on a server, print it on a machine there, where they're going to receive the paper. And then imagine that those guys have a bunch of printers, and everybody's printing to that machine, and then they're just picking up all the papers that came. So
Wait, who's the they in this situation?
Program committee chair.
Oh, so you're... Wait, you had the technical capability to print papers remotely at their offices and not email them?
No, anonymous. You need to.
It was, remember I asked you guys for printouts? There is multiple actions on my part to open your attachments, see whether it is fine, see whether it prints. I can't tell you how many times these things go wrong. The PDF is wrong, your printer is not, so if they've automatically, again, typically the program committee chair didn't allow that. So what you said was, oh, the guy in Berkeley, I've got a friend in Berkeley, so I'll print on his printer and he'll give it to the program chair. So, but yeah, you're right. This is a very concocted example, and that's why people don't have output.
So this is unspecified client, one or more, like a zero, one or more, to an unspecified number of servers.
Not entirely unspecified.
One server, specific, but you don't know which one it has.
Yeah, you're just printing in Berkeley.
Okay, you just can't.
And
So it goes out.
It goes out, you just say out. Again, I'm stretched. I'm hard pressed to come up with examples. That's why I started off by saying, theoretically, I can draw these arrows. Practically speaking, it's not that useful. Okay, and it becomes really useful when you go to 2. Okay, and all your examples, I can go and give a search query, and whichever is the next server can go and execute the query and return back the result. And this is, all these issues that we're talking about, scalability, etc. Okay. Now, this is not how people implement it. People implement it as an input port where these guys talk to each other. Okay. So,
sorry, in this example, do servers make responses intended for specific clients?
yes, the answers always go back to answers are always unidirectional. They don't go back. Yeah, absolutely. It's either a reply or they go and say this client. So this is a wonderful thing, right? You would think that this is what distributed computing is about. And you would think there'd be implementations of free ports. But there's none that I know of. They do what you guys were talking about. Where actually this is an input port, and all these servers talk directly to each other and do this. So why do you think that happens?
It avoids a single point of failure.
It avoids a single point of failure. That is true. But if you had instead a server input port here, and that server was farming out jobs, the same situation, right? So rather than having the port do it, you typically have a server with an input port, which has links to other servers and says, okay, I'll give it to the Indian server, and I'll give it to the US server, I'll give it to the Californian server, But that in general is always an issue. Let's go back to your question. Where does the queue reside?
In this case, it would be very helpful for the queue to be distributed among servers.
No, if it's distributed, it's for fault tolerance. But then how do you queue things up? Some kind of,
You have to have some input. You have to have some single input point. So
I'm sure there's.
Work hard.
No, but you guys already gave that answer before.
no, you just have your own machine. You have a separate machine that has it.
Okay. So let's go and talk about what happens, which machine has the queue. I'm going to answer the question that you guys were posing to me. Okay. In the case of input port, okay, there is a distinguished server, multiple clients, so here goes the queue. Right? And so message sent from client to server, there's one hop. In the case of output port, that's your distinguished machine. And, maybe the server just blocks and gets back a return. So there's only one hop. Otherwise, like you were saying, you send a notification saying, look, I'm ready. And then whoever sent the ready message first gets the message. So maybe there's more messages, but you could do it with one hop if you had some kind of blocking receive. Okay. And duplex free port, there's no distinguished client or server. And in general, queue is remote from both the client and server. So there's two hops. And that's one thing. And the other thing is you might use some kind of load distribution algorithm. You might do something application specific. So people don't implement it. But conceptually, it's a great idea. And maybe there are implementations. I don't know.
I know for the load balancer we had from some company called F5, and it was like very dumb, but it was a separate box, and the initial HTTP request, it would just round robin them to the server. So it was just like as fast as it could get that request off the load balancer and onto an actual web server.
Yeah. So and you wrote some code yourself to do that. Underneath it was all sockets, most probably.
No, this was just something that we bought.
Yeah. But it was not part of the IPC mechanism and probably some application-specific code that was using some lower-level IPC mechanism.
Yeah, they were probably as low level as you get.
Yeah.
The thing needs to be so fast.
But conceptually, this is, you can see that there's something like this you would want, maybe with some application-specific hooks, okay, and maybe when it's all in one server farm, that hop cost is not application. Okay. So now let's go to the examples that we were thinking of, where it's actually broadcast. So you have again the same kind of picture, but now each message can go to multiple places. It's not queued. It's not only one consumed by one process. And how would you define? So in output port and free port, message is not broadcast. So the question is, what would broadcast mean? So there are clients and servers.
Yeah. So if a client sends a message, and then when all servers check their mailbox, they all see message one.
They all see the message. Any other semantics for broadcast? And what would be a good application for that? And we've said many of them. You can just repeat them. Your software update.
Yeah, that would work.
Okay. And that would actually be. That would be an output. I mean, that would be a special case where only one sender and multiple receivers. Okay. And the other examples you had were.
A news server would do the same thing, or a news. In this case, I guess the
news client would send to a bunch of news servers.
To, like the port, and then the server would be the thing on my phone that tells me what to use.
And what about your? I know you're tired of the project. What about your project? The latest project, or Dropbox. Which is the client, which is the server?
Whoever picks something new in the folder would be the client.
It depends which step you're talking about.
Yeah.
Because you're talking about where all of the when it's downloading, get everything in sync. In that case, the Dropbox server is the client in this case, sending it to the central queue, which represents, or to the mailbox then becomes your folder structure, and then all of your machines, which are now servers in this example, check the mailbox and download any missing pieces.
Or just take Dropbox without the web server. Imagine, there was this live mesh from Microsoft that did that. There was no server. They just talked to each other. They kept the data consistent among themselves. Or your games. There's no server and client there, right? You just need something for latecomer. But logically, every client is sending to every other client also, right? There's no client-server dichotomy. You just want a bunch of replicas to be kept consistent. So you can imagine two variations here at least. And again, they're all, from their point of view, they're all equal. the servers themselves are all equal. And so a message from client goes to multiple receivers. In theory, you could have single sender. Okay, that is your software update example. But I just put that all together, and I'm calling this a multicast broadcast server. So message from server goes to specific client in general thing. And example, we've seen all these examples. And fault tolerance is a very good example, also thing also. So not only for availability, but also for fault tolerance. See, that's what we're doing. But for games, etc., I'm calling that a session port. Okay, where all the processes are equal, and every message sent by one process goes to all the other processes. And this is something that you guys have wanted, and you've implemented through a server. But you can imagine that being part of the IPC mechanism, and underneath there is, the implementation might use a server, might not. Okay. So we have a session port. Message from process goes to everyone else. Reply goes back to the sender. An example, multiplayer game, replicated file system, all these examples.
Yeah. What would that reply look like in the context of the game?
So in this case,
Nothing else.
I guess so, right?
that's
It's like, oh, I'm timing out. I didn't manage to send or something.
okay. So that is a very good thing, because when you talk a reply, you're talking about a request having been sent also. So I sent a request to say add 2 numbers, right? And it went to everybody. And this is a question not only in this case, but also the previous one. What is the result of that? And what do you guys think? I mean, I actually have built this into the system you'll be using this. I've got a session port, I've got a broadcast port, and I had to wrestle with this issue. That what does it mean when there's a reply, in the case of multicast? And what do you guys think could be the possible semantics?
The only thing I can think of off the top of my head is the acknowledgement thing. That's usually
No, but I'm saying add 5 plus 5.
Like you're telling them to do some processing and you want the result back.
So you could go and take the first answer that comes back.
You can compare.
You could go and take a voting to say how many answers with one particular kind. In my case, and I had to deal a lot with proxies and so forth, the result always has to be object. If you're going to do that, I send back an array of all the results. And now you can do whatever you feel like. And this will only work if the return type is object. Because otherwise I just can't go and put an array when it's expecting an int. Okay. So that's a very, very, very good question. Okay, people really haven't built these ports, but having gone through this theory, I said, okay, when I'm implementing, let me go and try to implement all these things so that I understand at least what I'm explaining. So.
But in that case, what happens if one of the processes goes offline before it has a chance to send its reply? Does it just block?
So then there's many things here. There's the fault tolerance one, and there's the non-fault. There's all kinds of things. And in one case, you get back whatever you got back. You wait for all the results. In some case, you just return.
So you just have a timeout that says that.
Yeah.
Just look at how many responses I got in this time frame.
Yeah. So that, and again, I wasn't making any policy decision. So you could just plug in whatever a little object that made the decision. So systems guys, are really the president is, the buck stops always the president, right? So they take responsibility. Systems guys always don't take responsibility. And they say, we are mechanisms people. And you are policy. So we're not going to make decisions. We just give you ways to do everything. And so I took the systems hat on. Okay. Okay, so we saw that just that one issue, access routing. There's, bound port, input port, output port, free port, broadcast port, session port, and each of them could be simplex or duplex, and the duplex could be just pure reply, or it could go and send back a message directly. Okay? So there's all these variations. And, this taxonomy is good. You can create this very flexible system like I've tried to do. And it also is useful in understanding what we've already learned. So among the various systems that you've learned, and we saw these points, Xenu, pipe, sockets, NIO, RMI. What kind of ports were supported there? So let's go one by one. This is Xenu. Okay, this was the simplest IPC mechanism. We even saw its implementation. Okay, it was only on one computer, but we at least saw how that was implemented. And you said, they were all threads called processes in Xenu, and you said send, PID, and some int value. And this guy did a receive, and he got back that int value. And in this case, it blocked. In this case, it pulled. Okay. So what kind of port do we have here? Is it duplex?
No, it's simplex.
And what kind?
I forget which one the first one.
How many senders do we have and how many receivers do we have?
One sender. You specified, right?
No,
Oh,
you can have multiple senders to the same.
Yeah.
Um,
But one
Okay. Multiple senders to the. How many input ports does each process have? One. Because the PID is the port ID. Okay. So each thread process has a single built-in input port, and this is just connecting to the monitor. So you don't have to go into create port. This is just simple that way. The Xeno was meant for simplicity, and not duplex, but sender can be sent back a message on its port. Every process is guaranteed to have a port. So that's nice.
achieve duplex without
Huh?
actually having to do duplex.
Yeah, you can achieve the results of duplex port. Except that the receiving process has to know whether it came back as a response to something they send or as a unilateral message.
You have to put a lot of information in that.
Yes, terse. Okay, pipes. Is it a simplex bound port? Producer, consumer?
Yes.
In fact, you're asking the questions, right? Makes it feel.
Absolutely.
You could have a name pipe, which has name.
If you guys remember, from our pipe description, a pipe is a file descriptor. And what happens to file descriptors? Do they ever get shared?
Yeah, I think that's
You
what
technically
I
run
did.
multiple senders to the same pipe.
And multiple receivers too?
You can also have multiple receivers.
And depending on, so in fact, the children processes may or not even close the descriptor. You can create a pipe and the children, and each, the same process could send and receive. Okay, the pipe abstraction allows that.
I guess the pipe itself is multiple.
So it's a duplex free port as long as they're all on one machine. And nobody ever uses it that way. It's used as a simplex bound port, but it's actually a duplex free port. Okay, and this is where you see that what is possible is far more complicated than what is necessary. And maybe these pipe descriptors should not be inherited. But actually, they have to be inherited to make it work for the shell. But maybe after that, they shouldn't be inherited. And maybe it's a non-issue because people just don't abuse it. Okay, sockets. You can answer this question. You're going to ace the exam.
Well, it depends on what level of abstraction you're talking about.
Sockets. What you used? I mean, Java socket. So you guys haven't quite used sockets, but we studied it sockets, right?
A socket is one-to-one duplex.
Duplex. The answer is so complicated that you know exactly why sockets are so complicated. There are many kinds of sockets. Right? There is the server socket. Right? There's a stream socket. And there's datagram socket. And that's why it's so confusing, because you don't know which one that one is.
I was thinking.
Yes.
That's just crazy.
But that is why sockets are confusing. It's one abstraction that has multiple roles. So a server socket. Duplex input port. I have a server socket, can listen to message, connect requests from multiple clients.
Can you ever send anything out from server socket though? Because I've never used them to accept connection.
Well,
I guess
yeah,
technically
yeah.
you reply, it has an act like this.
But it replies with the socket that creates a new. So the server actually gets back client information, so it can use it to establish something.
Yeah, what I'm getting is like you just can't send arbitrary data
out.
No, you can't. You can't send arbitrary data for sure, but you get back the connection handle. You can say, okay, you block, and you can think the status, one word status saying, so you can think of it as simplex too. Okay, but I thought of it as duplex just simply because
there is information.
Is I just want to make sure I've got the terms, all that. Is duplex import, is that redundant, or what two different things is that?
No, duplex means I get information back. Input means multiple clients share one mailbox. Okay. So what you were thinking of was the stream socket, and then you're talking duplex. And Java it is that way. Okay, but again I got a question mark there. In Unix, socket is a file descriptor. And so I don't know how Java implements it, whether it's still, whether the children processes get some kind of thing there, but at least that definition. So, and then datagram socket is actually a simplex input port. Okay, you've got a mailbox, multiple people can send messages to you. Okay, and anybody can send a message. In fact, you don't need, there's no need to create a server socket. And each client can also create a simplex port, just like in Xeno. You can create another port to receive messages. So I think we understand things a little better with this terminology now, because there are three kinds of sockets.
So a stream socket would definitely be three port then, because you can have like its input stream, like the input output streams you get from it in Java, you can send local threads. So
yeah. So are the threads considered consumers? So that's considered just all one big process. So the question is, but in Xeno, if a socket in Unix can inherit a different address spaces. So yeah.
So the socket, the stream socket, isn't a one-to-one connection.
Not in Unix. It's just a file descriptor. It's a file descriptor. Your children just get it. That's how people often farm out work. That they just exec a process that reads their contents. That was the motivation for this. That they fork or exec a process, and they pass it. It gets the connection, and it services the connection. And everybody else thinks that they're talking to one central process, but actually the central process is farming out children.
No, but the server, when it does, let's say, receive from a client,
Or a client does receive from a server, either way.
yeah, but I'm just talking, you're saying that multiple clients will connect to a server, but the server will have individual software instances.
Yes, but it'll have different. Yes. And then the client can fork another child which actually produces the information on that connection. And the server can fork another child which actually consumes on that. And all the children can consume from that socket. And all the clients can produce information on that socket. It's like shared file.
it's just treated like a file. You can fork a process without any trouble.
Right,
That's
but
the file
those
descriptor
are
socket.
concepts extrinsic to the concept of socket.
Sorry?
But all of those things are they're external to stream sockets. That's not part of stream sockets. That's part of something external.
What are you saying? That's just using the implementation.
No.
I'm saying that using the stream socket, I can only send data from one port to another port. And
No. One. You send process from one process to another process. Socket is the port, right? Socket is the port. And it was designed, sockets, this was the big innovation behind sockets, guys. Before this, IPC was distinct from file systems. And everyone had their own IPC system, and they were fighting over which one is best. And then came Berkeley Unix, and they said, we are going to make sockets as file descriptors. And every other effort just died. Some gradually, some later. This was the main concept. They said, we are just going to use file descriptors, and the examples that were given involved some process, server receiving a message, and some process establish a connection with another process, and then forking off children to actually service those requests. That was the design That was what they were.
What the whole concept behind file descriptors, but the file never receives anything unless it's being written to it, in which case it will have a one-to-one thing.
No, multiple processes can write to a file. I can write the first byte, you can write the second byte, I can write the third byte. That's what file descriptors allow. You can have a stream opened by multiple processes.
For writing.
Yeah.
So there's no read-write blocks implemented.
You can have. So there's many abstractions possible. One is, I'm a process, I opened a file. You're a process, you also open that file. Okay? I have one pointer to the file, you have another pointer to the file, and if we're not locked, I'll overwrite yours or you'll overwrite my file. Okay? When whoever closes first is going to win. The second semantics is that we both share the read-write mark. So I write the first byte, you write the second byte, I write the third byte, you write the fourth byte, and when we close, our data all gets coalesced. Similarly, I can have multiple processes reading from the file. I get the first byte, you get the second byte, third byte, and that's when they're all children of the same process. If they're all reading independently, then it's one or the other. Then they're not sharing read-write mark. Okay, so in the operating system table, there is a read-write mark table, then there is an inode table, and your file descriptor points to the read-write mark table, which points to the inode table. Okay, so when two different processes go and share the same file, they go from two different read-write marks to the same inode. When two processes share a file descriptor, they go from two file descriptors, logical file descriptors, to the same read-write mark and to the same inode. That's how it works.
Right, so I get that they go to the same logical first and then go to the OS. Because I think otherwise the OS would block. It can't have to write two processes writing to the same file.
How does it care? It's a file. It just needs the right call. It doesn't care where the right call came from. So, okay, I got to put a byte into this file. I'll put this byte. I'll put this byte. What is it? It doesn't care. It's you who cares as an application programmer. OS is fine. They're all the same.
So as an application programmer, if I open a file with requesting write permissions,
Fine.
the OS will give you write permissions even though another process may already have write permissions.
If it's not locked the file. Okay, if you notice that in your Windows machine, Notepad++ does not lock the file. Okay, whereas Word will not lock the file. So it just depends on the application whether it locks it or not.
Yeah, Notepad will prompt you if the file has been
modified,
saved or something. Yeah, it lets you reload it.
Yeah. It doesn't block. It doesn't block it. So that's a separate issue. But even when the process has locked it, its children can get it. That's the main point.
Children thread?
Children processes. Threads, of course, they can get it. Okay. Okay. RMI, input port, output port, free port. If you've defined a remote procedure, how many people can call it?
As many as need be.
So
And ultimately, it's called in the same object.
So it's basically a duplex input port, right? But you can imagine simplex bound or output port. You can imagine just two-party RMI. For all the applications that we were talking about, it didn't matter whether it was procedure call or not procedure call. Okay? So people don't build it, but conceptually it makes sense. So in the system I built, you've got all of these choices. Whether they're useful or not, I don't know. But you've got the duplex RMI, you've got the simplex RMI, you've got the free input port RMI, you've got broadcasting RMI, all of these things. Okay. So we've just figured out how messages are going to be routed. We haven't said what it really means to produce a message and consume a message. And is RMI really message passing? Yeah. And so this is message passing, as you know. Okay, you're saying send port and you're sending a value, and here you're receiving the value. Here you are calling the procedure. So, but we can talk of duplex, simplex, free output notions, regardless of whether it is Xenu or it is RMI. That is a question of how many parties are involved. So it does make sense to go and unite them together into one framework. So that's why I put that into message passing. And if they're both message passing, then what's the difference between this and this? Sorry? So the semantics here is a procedure call.
On an object that's not.
Yeah, on a remote object. And what the semantics here are? So
Every processor is capable of sending something.
So this is a remote procedure call. This is a remote
Remote process. It's like,
what's
That's synchronous, this is asynchronous.
no, that's another issue. We'll get into that. You can have asynchronous procedure calls. This is a remote procedure call. When we teach programming, students want to do no procedure calls. So what does a student do when they first start programming? What's the construct they use a lot of? Sorry? This is a remote. How is it a remote assignment? That's you got it. What am I doing? What does a matched pair of sends and receives here result in a method being invoked, right? A matched pair of sends and receives result in int expression being assigned to a LHS assigned an RHS value. Essentially.
What was that last one?
You know, in LHS, left-hand side and right-hand side of an assignment. So right-hand side is always an expression, and the left-hand side is always an address.
Right.
So whenever you do a receive, you also always got either you do it this way, with the return value, or you got to have basically an address buffer. And when you send, you just need an expression, something with an R value. Right? So this could be 5 plus 7 plus 8. Right? Whereas this has to be an address, an L value. So L value is an address, R value is just something that's just something you stored at an address.
Okay.
Okay? So the send semantics, so we see that there is messages being produced, there's a message being consumed, and I just use these pictures to show that without committing myself to what happens. And message consumption. So what does it mean for a process thread to consume a message produced by another processor thread when you're using inter-process communication? Right? Inter-thread communication. And remote assignment. Message is data to be remotely assigned to a variable. That is essentially what it is. Okay? So there is a variable declared in the receiving process. There's an expression that is stored in the mailbox. And when that message is received, that expression is written on the variable. That's the way I'm understanding it. Okay? And the result of send is to assign a sent expression to some variable in the remote process. Okay, I got to correct this English here. And the type of expression depends on whether language support is provided or not. So if it is an OS, it might just provide you bytes. And if it's programming language, it can say this is a typed variable. You can only send 5 or 7 or 8, depending on the type of the port. Okay. And I'll stop here, but you guys heard of CSP, programming language?
Communicating sequential process.
Yeah, it's the landmark language in this whole field by Tony Hoare. And this is the syntax. It was about, they always had bound ports. I should have had P and Q here. So this says, send to process P this expression. And this one says, receive from process Q a value that's assigned to this variable. So the next value that I receive from process Q should be assigned to this variable. I should have had P and Q. That's what he used, Tony Hoare used. So you're sending out an expression that's assigned to a variable, and this language made it very explicit. Okay? This is the landmark language. I mean, people used to talk of Hoare's language and all these. Before sockets, I mean, there were all these contemporary languages. Okay? And we'll just stop here, and we'll see procedure call next time, which of course you understand.